Hi, this is Professor Fernandez, and we are going to talk about class notes B in lesson 4. Let me scroll down here to show you where we are heading toward. So our goal is going to be to derive this ODE model for the mass-spring-dashpot system. Let me scroll up and show you some of the assumptions that we are going to start off with. So I described these in this paragraph up here, and I'm going to run through them in detail down here. So first thing I'll do is I'll draw a schematic, little diagram of what is going on here. So we have this mass hanging from a spring, and the displacement from equilibrium in the vertical direction we're going to call y of t. So when the mass is hanging at equilibrium, it's not moving, that is going to be y of t equals 0. And then we are going to consider the direction, down to be positive direction. So if we were to pull down the mass, for example, and get something that looks like this, a little bit past equilibrium, that would be considered a positive displacement. And that would be y of t, that's positive. If the mass were up here somewhere above equilibrium, then that y of t would be considered negative. So that's what we mean here by considering the direction to be positive when the mass is below equilibrium. Okay, the second thing is I had mentioned in this paragraph above a little discussion about the fact that the damping force produced by a dashpot, remember this goes back to the application in the beginning of the lesson, resembles that of Hooke's law and depends on the velocity of the system. So down here are the mathematical details. So I'm going to call this damping force F sub d, and just like Hooke's law that we considered earlier, it has a magnitude. So the magnitude is proportional to the velocity, that's y prime, since y is our displacement. And it is equal to the velocity times some positive number. So this is, again, a simple model of the damping force. So that's the magnitude. And it also has a direction. And just like Hooke's law, this damping force opposes some aspect of the motion. In Hooke's law, it was the opposition of whether the mass is below equilibrium, then the restoring force pulls toward equilibrium, or if the mass is above equilibrium, the restoring force pushes you down. In this damping force, the mechanism by which the system tries to restore itself is all about motion, not about relative to equilibrium where the mass is. So this is going to be more about if the mass is moving up or if it's moving down versus if it's below equilibrium or above equilibrium. All right, so with all that said, let's get down to the nitty-gritty of understanding how all these forces act. And I'm going to run through this table that I've put here to understand how these forces interact. The first thing I'll do is I'll draw a few diagrams. So just to notice one thing, the first two rows in this table are about the above or below state of the mass relative to equilibrium. So I'm going to draw the original mass at equilibrium, and then right next to it, I'm going to draw the mass below equilibrium, and then I'm going to draw the mass above equilibrium. And we're just going to analyze, using Hooke's law, what happens in each one of these cases. Okay, so the way this table is set up is, first column here, I'm giving you the physical state. If you went into a lab and you tried to see what this system looks like, this is what you would see. You would make observations of the form, it's above equilibrium, it's moving up, it's moving down, right? Those sorts of things. If you then try to translate those observations into some mathematical form, this is what you might come up with. Some information about the y, the position of the mass, some information about how fast it's moving. And then given that information, right, we know what the restoring force, the magnitude and direction, and what damping force, magnitude and direction are. So we should be able to deduce from its mathematical state and the form of these forces what the actual terms of the force are. So that's what I'm going to do here. So let's get back to these three diagrams. So here we are at equilibrium. Suppose I pull the mass down. So we are here below equilibrium. So that's the physical state. Now what's the mathematical state? corresponding to this state of the system? Well, so the mass is below equilibrium. If I go up to my assumptions, right, down is the positive direction. And I'm assuming that y is the vertical displacement. So in this below equilibrium state, this is y of t, and because down is positive, that means that y is positive. Great. And then I'm thinking only again about above or below equilibrium for now. So if I go back to Hooke's law, what would Hooke's law say? Well, it would say if I am below equilibrium, the spring has been stretched. The restoring force is going to want to restore the spring back to equilibrium. So the restoring force in this case points up, and that is opposite the direction that we considered positive, which was down. So in other words, the restoring force is negative. So if I go back here and I try to figure out how to put that in mathematically, express that mathematically, this is what I come up with. Why? Because let's do the analysis here. We just determined that the restoring force should be negative. Great. So let's look at each one of these terms in this expression. So the negative sign is negative. Great. K is positive. Okay, still negative. And then to keep this product negative, y has to be positive. And that is indeed what we determined from the mathematical state here. So that's why this restoring force term has a minus ky in front of it. Okay, so then I'm going to redo the entire analysis here to see if anything changes for this picture when the mass is above equilibrium. So here, this is the displacement y of t. The mass is now above equilibrium. Because it's above equilibrium and because our coordinate system has the positive values below equilibrium, then the mathematical state corresponding to this physical state is negative y values. And then I'll do the similar analysis. So if I go back to Hooke's law, the spring here has been compressed, and the spring does not want to be compressed. So it wants to stretch back to equilibrium. So the restoring force here points down. And in this case, right, that is in the same direction as our positive coordinate system, right? So I want the restoring force to be positive. So it has to have this form. And let's analyze this, right? Minus ky. So you might think, well, there's a negative sign here times k, which is positive. Well, this product is negative. That's true, but remember that the mathematical state in this scenario has y negative. So we have a negative times this negative gives you a positive, right? So that is why this particular row also has minus ky. Okay, so we'll make some conclusions about this in a minute. But let me go back now and analyze the last two rows in the table. And the picture there is one about moving up or moving down. So I'm going to draw a slightly different picture, and I'm just going to forget about equilibrium for now, because again, this part of the story is just about in which direction is the mass moving, not where it is relative to equilibrium. So let's suppose that the mass is moving down. Okay, so in this case, the mass is moving this way. Great, so that happens to be a place where we need to think about this damping force and which way it would point, right? So we had said up here that this damping force, and you can think of this as air resistance, it has a very similar form, opposes the direction of motion. Opposes the direction of motion. Okay, so if we're moving down, then the damping force here is going to be up. So that's the direction of the damping force. And then similar analysis as before. Since the direction is up and our coordinate system is positive in the downward direction, then that means that this force is going to be negative, right? It's going to be opposite the positive direction. So we want the force to be negative. Okay, great. So one thing I mentioned I didn't do here, let me back up, is talk about the mathematical state. So if we're in this setting where we are moving down, let's talk about the mathematical state here, jump back a bit. we're moving down. So what's happening? The y values, which are positive going down, because the mass is moving down, the y values are increasing. And we know mathematically that an increasing function has a positive derivative, right? So that explains why y prime is 0 here, y prime is positive here. Okay, so then let's go back to our damping force. We left off realizing that it points in the opposite direction of what we have deemed to be positive. So we want the damping force to be negative. So then we're going to come here and see if this is in fact negative. So we're going to analyze this term, minus cy prime. Okay, this is negative, check. C is positive, so it does not change the fact that it's negative, check. And then y prime is positive, check. So the product of these three terms is indeed negative, which is the place, the direction we want this damping force to point. So we do get the correct direction and magnitude by keeping it in that form. So now we'll redo the analysis for the mass moving up. So let's talk about that. Okay, so here is our mass. Let's now suppose that the mass is moving up. Okay. Similar way to start the analysis as before. The damping force opposes the direction of the motion. So this damping force is going to want to push the mass down. Again, think of this as air resistance. So it's wanting to push the mass down, which is in the direction that we have said is positive. Okay, so we want this force to end up being positive. All right, great. And then we are assuming that the mass here is moving up. So the y values, whatever they were, the mass is going to be here a little bit later, and then be here a little bit later, and then be here a little bit later. So the y values are going to be decreasing, right? Because again, values below equilibrium over here are positive, values above equilibrium over here are negative. So a function with a decreasing y value is one which has a negative derivative. Okay, so that means that y prime is negative here. So that's our mathematical state. And then we go back to analyzing the damping force. So we said it's moving down, same direction as our positive direction, so the damping force is positive. And then we go and analyze all the terms here. So let's look at minus cy prime. This is negative, so we don't want that. This is positive, so that doesn't change anything. But then y prime, we said, is negative. So that fixes everything, because we have this negative times this negative makes it positive. And the c is already positive, doesn't change anything. So the outcome here is a positive number, which points down, which is our direction for positive. So that explains why this last row has minus cy in it, just like the second row. So then let me now talk about the takeaway from this whole analysis. So what is the takeaway? Erase some of these things here. So the takeaway is that if you look at the first two rows, the restoring force from Hooke's law is exactly the same. Has the same form, has the same direction, has the same magnitude. If you look at the last two rows, right, so first two rows here, the restoring force, exactly the same. If you look at the last two rows, then the damping force has exactly the same form, minus cy prime. So we can now write down from Newton's second law what we expect for the mathematical model. So mass times acceleration equals the sum of the net forces, right? And in whatever case we're talking about, below equilibrium, above equilibrium, the restoring force is minus ky. In whatever case we're talking about, below, moving up, moving down, the damping force is minus cy prime. So these are the sum of the net forces that we're considering in this particular simplified model. And what do we do after that? Well, we put the ODE in standard form. We try to effectively get all of the functions and their derivatives to the left-hand side. And that gives us this model, which is exactly what we wanted to derive and is down here. So that's the end of our derivation.